Hi everyone, welcome to our facial feature detection project. So this is our outline. First of all, we'll go over the data, talk about some exploratory things we've done. We'll talk about our related work, show some methods, and then explain the experiments we've done, and then show the system and how we organize our project structure, and then give you guys a conclusion by giving you guys a demo. Here's an intro to the data. The data set is celebrity faces attributes. There are over 200,000 faces and unique, and there's only 11,000 unique identity, 10,000 unique identities. But the names of the identities are not given. There are 40 binary attributes, 5 landmark locations, and each image is 178 by 218 dimensions. As you can tell, the data is not quite balanced, but we will ignore that for now and do some analysis. So here is a quick look at the data. As you can see, some of the faces aren't facing forward, and that is an inherent problem in trying to classify, making a CNN image classification. So one thing we'll try is using hard cascades to process the image and make sure each faces that are not facing forward, we filter it out and we replace it with a more cropped version, zoomed in on the face, removing most of the graph background so that we could have a much clearer and cleaner data set to review. So here's a quick look at the code. There are a couple of parameters that of our interest. First of all, before processing any image, we need to convert the image to a grayscale image. And then the next parameter is basically the passing parameter. So basically since hard cascades are trained over set size, if it can't find the set size image, it needs to resize and go smaller and smaller and pass it on the same image over and over again to detect if there are any faces. So 1.2 means it passes every time it can't find a face, it resizes the image, makes the image 20% smaller and tries to find the face again until it finds matches. TOL kind of stands for tolerance. Basically, it's like the reject level. The higher the tolerance level, the higher the chance that the lower the quality. The higher the tolerance level, the lower the tolerance level, the lower the quality of the image. So sometimes you will get side faces, where sometimes you'll get non-faces. So for our project, we set the tolerance level at around 20. Minimum size is basically the minimum size of your output image. So anything below 60 pixels by 60 pixels, we will not classify as a face. So this is our code, and then we basically show the results of what a crop face will look like. Now, for our ideal vision is basically creating a app that for the end user, and we want to select certain features for the end users to use, such as whether they may want to know if they're attractive or not, or they may want to know if the machine could detect whether or not they're smiling. So we isolate these features and train individual models on some of these select features, preferably the most balanced features. So one question is what model and architecture we should use. We've experimented with different models and architecture, including LENet. LENet is very, very archaic, and it works on the Minis dataset really, really well. However, for large-scale image recognition and more complex structures such as attractiveness, you need a much more complex system to analyze everything. So in this case, we use ResNet, and specifically in our paper we will publish more. We will show you guys results on each accuracy level on each of the architectures. We experimented with VGG, we experimented with Inception, and ResNet 18, 34, and 50 on our paper. And we ended up finalizing our models with ResNet 50, as it is generally the fastest and also and it does not compromise accuracy. So here are some of the selected toolkits we use. At first, we use Keras and TensorFlow to explore models, to basically build a preliminary model and see and analyze the findings. And we found that although Keras and TensorFlow gives the user a lot of control on the data and allows them to set hyperparameters at a very more concisely, it lacks speed, and it also lacks readability, and it also lacks efficiency in terms of the number of lines of codes you type. So we resorted to using FastAI and typing everything in FastAI, since it requires less effort and you could train multiple models with less lines of code. More on this will be available in our paper. So basically, first of all, to make a FastAI, to initialize a FastAI object, we need to first filter all the labels as well, because after extracting the images, our labels data set doesn't have all the images, the removed images removed. So we quickly go over all the images that have been removed, remove them from the data set using these code. Then we train our data set by first initializing a data block. We initialize my data block by passing in our labels, and then we split it by we split it by training and validation by a certain percentage. For our experimentations, we split it by 20%, but for production, we will split it by 95 to 5%, because we want to maximize as much training data as possible. Label from DF basically tells you which column is your label, your y that you're predicting. And then we pass in a couple of transforms. In our paper, we've gone over different transforms and different hyperparameter tunings and identified that this is, although this may not be the most optimal hyperparameters, it is pretty optimal for our case. So some of the transformations we included are flipping. We do some horizontal flips. We change some max lighting. We do some rotations by 10 degrees. Max lighting basically means the contrast and brightness could change up to 20%. Max warp is kind of interesting. Basically, it makes certain parts of the random parts of the image bigger, like it zooms in on certain parts of the image, and then it basically just distorts the image a little bit. So for most of the models, max warp has a benefit by making the model more robust. But in terms of attractiveness, it actually decreased our accuracy of the model, since by warping the faces, it basically biased the attractive level we're trying to predict. And max zoom basically randomly zooms it by around 10%. So we initialize all of them, we bunch it, we put it all together by using the calling bad bunch, and then we normalize it by by subsampling some of the data and finding its mean and standard deviation of each pixel value of each color channel. Here is a quick look at all the data. Attractive male has around an accuracy around 80% after 5 epochs. The time used is a lot less, because since we subset it, attractiveness by male and female, so it's a lot less than the other models that we will show. Here is a quick look at attractive female. Accuracy is a little bit higher. This may be because of bias. And then here's a quick look at bags on the eyes, around 84%, bangs around 96%, eyeglasses around 99%. Some of the outputs on Jupyter Notebook did not output fully, but we will still include the partial output. The model has been fully trained. Here's male versus female, mouth slightly open, smiling. And then here's a quick look at how our model looked like, and some predictions using the validation set and an actual testing set, my face. And then after that, we want to basically bundle all this together and give it to the end user. Our first version of trying to live predict a face is using OpenCV, and it basically opens a box on your Windows or Mac computer and lets you do live predictions. However, this is not enough, so we want to do live predictions and host it on a server. So we made another version and basically hosted all of it basically converts the live images as still frames, change it into JPEG, and then change it into bytes and passes on as a JavaScript object to the web page.